Welcome to the Explainer. Okay, so today we're diving straight into the heart of advanced mathematics. And I know if you look at massive calculus equations, they can seem super intimidating at first glance. But a closer look reveals they aren't magic at all. In fact, they rely on this brilliant, highly logical process of reverse engineering. We're going to break down how some of the absolute most complex math concepts are really just familiar tools that we're using in reverse. Think about it like these calm, expanding ripples moving outward in a pond. Our mathematical knowledge compounds in the exact same way. You drop a single pebble of foundational understanding, say basic addition or a simple derivative, and those core principles expand outward. They intersect and layer on top of each other to solve incredibly complex, real-world problems. We aren't just learning a bunch of disconnected tricks here, we're actually watching a foundational ripple effect in action. To guide us today, we're looking directly at the gold standard of math education, the Cambridge International AS and A-Level Mathematics coursebook. Specifically, we'll be pulling from the sections covering Pure Mathematics 2 and 3. This curriculum is just beautifully designed to show exactly how those mathematical ripples expand into higher-level calculus. So, here is our roadmap for this explainer. We'll start by unlocking pure mathematics, move into the fundamentals of integration, spend some really good time on estimating with the trapezium rule, ask why study further calculus, and finally, look at advanced integration techniques. All right, Section 1, Unlocking Pure Mathematics, Building the Calculus Toolbox. Here's the crucial thing you've got to keep in mind. Mathematics isn't just about moving forward from point A to point B. It's a compounding language of reverse processes. To solve the hardest, most stubborn problems in engineering, physics, and beyond, we often have to look at an answer and think backward to figure out how we actually got there. Keep this concept of the reverse process in the back of your mind today because it is literally the key to everything we're about to cover. Moving on to Section 2, the fundamentals of integration, with an overview of Chapter 5. So in Chapter 5 of the text, the syllabus officially extends this whole idea of reverse differentiation. If you already know how to find the rate of change, the derivative, integration is basically just asking you to reverse that process to find the original area or total accumulation. And we aren't just doing this for simple variables anymore. We're stepping into the realm of complex exponential, logarithmic, and trigonometrical functions. But let's pause for a second, because the textbook asks this really brilliant fundamental question. Why do we even study integration at all? Before we look at the raw math, it's worth anchoring our motivation. We study it so we can solve physical problems that involve accumulation, whether that's calculating the total distance a rocket has traveled based on its changing velocity or figuring out the precise area under an irregular curved bridge arch. We literally need these tools to model the real messy world. Now check out the pattern in these specific integration rules for sine, cosine, and secant squared. Because the derivative of cosine is negative sine, the integral of sine gives us a negative cosine. It's a perfect mirror reflection. If you have a solid grasp on your basic trigonometry rules, you already hold the keys to integrating them. You literally just have to walk backward. Which brings us to Section 3, Estimating with the Trapezium Rule, when exact math gets tricky. This is a huge focus for us today. And this introduces a highly practical tool covered in Chapter 6, the Trapezium Rule. You see, in Chapter 6, the syllabus acknowledges a really important reality. Sometimes, finding an exact algebraic reverse process for an integral is just impossible. It happens. But instead of hitting a wall, mathematicians use this brilliant numerical backup plan. By chopping the area under a complex curve into uniform, straight-edge strips, trapeziums, we can calculate a remarkably close approximation. And the mechanics here are wonderfully simple. To find the width of those strips, which we call h, you just take the upper limit, b, subtract the lower limit, a, and divide by n, which is the number of strips. A huge takeaway from Chapter 6 is understanding this inverse relationship. The more strips you create, the smaller your h gets, and the tighter and way more accurate your approximation becomes. It's an incredibly powerful workaround. All right, on to Section 4. Why study further calculus? Stepping into Pure Mathematics 3. So, Chapter 8 really escalates the complexity. This section is specifically designed to stretch the minds of Pure Mathematics 3 students. We are officially unlocking a whole new tier of the syllabus here, moving past the basic rules and looking at functions that require a bit more mathematical elbow grease to reverse engineer. The book poses another one of those philosophical resets. Why do we study calculus? Not just integration, but the whole system. We study it because the universe is in a constant state of motion and change. Calculus is literally the mathematical language of change. By extending our knowledge into further calculus, we are quite literally upgrading the resolution through which we can understand and predict the physical world around us.
And finally, Section 5, Advanced Integration Techniques, Reverse Engineering. This logic just brilliantly illustrates our core theme for today. In differentiation, the forward process, we use the chain rule for nested functions and the product rule when functions are multiplied together. But to reverse that, integration by substitution directly reverses the chain rule. And integration by parts, that is directly reversing the product rule. You aren't learning isolated, scary new concepts here. You are literally just learning to put your car in reverse and navigate the exact same streets you've already driven down.
So what does this new advanced toolkit actually look like? Well, for pure Math 3 students, it means recognizing complex patterns. You'll use the derivative of inverse tangent. You'll take giant, messy, rational functions and break them down into bite-sized, easy-to-integrate pieces using partial fractions. You'll learn to spot specific forms, like when the numerator is exactly the derivative of the denominator. It's kind of like becoming a mathematical detective, looking for the clues left behind by the forward differentiation process.
I actually want to highlight this quote directly from the source material because it hits the nail right on the head. Integration by substitution and integration by parts can be considered as the reverse process of the chain rule and the product rule. This single sentence perfectly connects months of study. It proves that advanced math is just an elegant, closed-loop system. So I want to leave you with this final thought as we wrap up today's explainer. If complex calculus is ultimately just a matter of learning to deconstruct a problem backward, how might mastering this reverse process mindset unlock entirely new problem-solving strategies for you in computer science, engineering, or honestly, even your daily life? Because sometimes, to make the absolute biggest leaps forward, you simply have to figure out how to trace the steps backward. Thanks for joining me today. Keep questioning, keep learning, and I'll catch you next time.